Hello everyone, I'm Heyu and I'm from Michigan State University. So today I will present my work about the electrochemical sensor for gas measurement. So first is about the gas sensing application. So gas measurement has attracted our attention because the very important role of gases in our life. But the air pollutants, for example, mainly from the industry emission and then explosive gases which can threaten the human life. So it's very important for us to develop some gas sensing technologies. So here, a lot of work have presented that they can develop wearable devices for gas sensing. So wearable devices that can provide a very rapid alert for human is very important for the safety of human life, and also if we can develop some gas sensing network, that would be awesome. So the most important thing is that a gas sensor on the wearable devices. So a miniaturized, a very fast response, and a very long lifetime. How can we achieve that? So here is a general comparison with different technologies. So I think as presented by the previous presenter, different technologies have different advantages and disadvantages. So with the electrochemical sensor, it has very good. So it has very good selectivity and low cost, and it's very easy for miniaturization. So we're trying to implement this electrochemical sensor for gas sensing. But electrochemical sensor has its intrinsic drawbacks, which is the maintenance. Because when we use the electrochemical sensor, we need an electrolyte, and the liquid electrolyte is very easily evaporate, and we need to frequent maintenance. And the other thing is that the response time, the gas needs to diffuse through the electrolyte, and the diffuse coefficient is very low, so it will take a long time. So for these two problems, we came up with some solutions. The first one is the electrolyte evaporation. We use the room temperature ionic liquid, which is a liquid composed of 100% of ions, and this liquid has negligible vapor pressure, which means this liquid cannot evaporate. And the other problem is that the very slow diffusion in electrolyte. So we're trying to use some porous substrate, which means the gas can diffuse through the substrate instead of through the electrolyte. So by this means we can improve the response time. So based on these two solutions, we propose this room temperature ionic electrochemical gas sensor on the porous PTFE substrate. So first, this one is a schematic of our sensor structure. Here shows the porous PTFE substrate, and then so in our design, the gas will diffuse through the backside of the substrate instead of the electrolyte. And then we use the photolithography to pattern the gold electrode and the titanium adhesion layer on the substrate. Then we coat the room temperature ionic on the sensing area. And this electrolyte we want to emphasize that there's no evaporation. So based on the previous design, we implement our sensor. So the size of our sensor is 8 millimeter times 6 millimeter, and also the substrate is flexible and attainable, so we can tailor to different size. And then the gap of the working electrode and the contact electrode is 120 micrometer, and then the size of the finger is 270 micrometer. So we also use the SEM to check the surface. The surface here shows the surface structure of our working electrode. So we can know that the surface is very rough, and we think this rough surface can enhance the sensing area, and also the porous structure can enhance the diffusion of the gas. So we have the sensor. Now we want to measure it. So generally, the method for gas sensing is the constant potential amperometry, which means we apply a constant potential on the working electrode, and then we record the current, and then we do the final analysis. So here shows the example. We use it for oxygen sensing. So the potential problem is that, so in this period, the sensor needs to decay, which means the charging current need to decay to a very stable stage, and then we will do the next measurement. So this phase will take a very long time. And the other thing is that, so the potential is always applied on the working electrode, and the surface of the working electrode is always reacting, and it will produce much byproducts. I think on the metal oxide sensor, it will something like poison the sensor. So the advantage of electrochemical method is that we can apply another potential, which means we apply two potentials on the working electrode, and we can reverse the byproducts. So we can overcome this byproduct accumulation. But also the general double potential method also need a very relatively long time, because we also need to wait for a long decay time. So here comes our new method. So we propose this new method to decrease the measurement time and to remove the byproducts. So here shows the stimulus of our electrode. We apply two potentials, the oxidation potential and the reduction potential, to react the targets and then reverse the byproducts. And here shows the output, the single output. And the double potential method generally use a very stable current here. So we are thinking, is it possible to use a transient current, which is set here. So before the current is stabilized, it is possible for us to use it. So based on the reversible reaction, we are trying to use the oxygen to validate our method. And what we want to mention is that, so this method is also possible for other reversible gases. So before our test, we want to validate is it reversible of oxygen reaction in ionic liquid. So we conduct the cycling voltammetry test, and from this result we observe the reduction peak of oxygen here and the oxidation peak of superoxide here. So from this result, we concluded that the reaction of oxygen is reversible. So we performed the transient dBA test next. So we tested six samples. Okay, here shows the parameter setup. We optimized the different parameters here, and then we performed the test. And from this test, we can know that the sensor can respond differently to different concentrations of oxygen. And then we extract the current at 1 second and 2 seconds, and we made the calibration, and it shows very good. Okay, we performed the 5 repeatable tests, and here shows the error bar. The repeatability is very good, and the linearity is also very good. So we can conclude that this transient dBA method is very it's good for the it's validated with good repeatability and linearity. And we want to emphasize that the measurement is only 4 seconds. And also we made a comparison with the calibration at 1 second and 2 seconds. It shows that the sensitivity will decrease with longer time, but the repeatability and the errors is decreasing, which means the measurement time can be further shortened if we can sacrifice some linearity and then error and the repeatability. So we also can perform the more repetitive tests to validate our method and our test. So we performed the 20 repetitive tests and the 4,000 repetitive tests in 100% of air, and it showed very good reproducibility, which is the relative standard deviation. And then we compare our method with the constant potential amperometry. So the test is performed with 5 gas cycle tests. Here shows the gas input. We alterate the nitrogen and 50% of air. And here shows the response of the constant potential amperometry and our method. So the difference is that the transient method will apply to 2 potentials, and the constant potential amperometry will only apply to one potential. So also we extracted the current signal, and we made a comparison here. So the relative standard deviation of the transient dPA is 1.65%, and the constant potential amperometry is 4.48%, and it's 63.2% decreased. So we conclude that this method is very effective in improving the reproducibility compared to the constant potential amperometry. So here is our conclusion. We presented an RTIL-based gas sensor with porous PTFE substrate, and then we proposed this new method, and we also compared our new method with a very conventional method, and it shows very improved reproducibility and a very short measurement time. And this work is supported by an NIH grant, and thank you.